So hi everyone. Today we have Haiyang Wang from Fudan who moved to Cambridge, who will talk to us about circumbinary accretion. So please go ahead.
Okay, thanks a lot. It's a great pleasure to be invited to give a talk here. And I'm Haiyang Wang. I'm currently in Cambridge, and I actually moved from Fudan in Cambridge to Cambridge last summer in 2020. And today I will talk about the mostly the hydro simulation of circumbinary accretion and perhaps a bit of linear theory to interpret our simulation results. Perhaps I can start with some very basic information about binary accretion. Is that it is very different from accretion to a single gravitational object, such as one black hole or one star. Is that for circumbinary accretion, we actually have three accretion disks. The first is the largest one, which is called the circumbinary disk, as you can show in the larger distance. And this circumbinary disk is gravitationally truncated because the gravitational field of the binary, and the truncation radius is around twice or 2 times or 3 times the binary separation. As you can see, inside this truncation radius, you have a low density cavity, and the accretion is operated through this narrow accretion streams connecting from the outer circumbinary disk to the inner circumsingular disk or mini disk. So in the end, you have 3 accretion disks, 2 small mini disks at the center and 1 large circumbinary disk at a larger radial distance. So this is a 2-dimensional plot. In order to show it more clearly, you can see in a 3D simulation, actually, well, you can see this kind of prominent spiral structure both in the small mini disk and the large circumbinary disk. Why are we interested in those circumbinary disks? Well, mostly because 2 reasons. The first is there are lots of galaxy mergers in our universe, and we expect most of the galaxies will host one supermassive black hole at their center. And after galaxy collide and merge, we expect that 2 supermassive black holes will also form a compact binary and merge within a Hubble time. This is called the final parsec problem because previously people thought that the binary will merge very fast, like within 1 million years or so, but later simulation results found that it is actually quite difficult for a binary supermassive black hole to merge when the separation of their separation is around 1 parsec. So this is called the final parsec problem. And the circumbinary disk is proposed to solve this problem because people saw the presence of circumbinary disk can extract the angular momentum from the binary and lead the binary to cause the binary to merge. We're also interested in circumbinary systems because they are observed in a lot of young stellar binary systems, such as the amazing observation made by 𝙰𝚑𝚎𝚗 or sorts. And they are rich in dynamical processes, and planet formation are observed to performing this kind of circumbinary disk. You can see on the rightmost panel that this kind of spiral structures are actually directly being observed in this kind of circumbinary protoplanetary disk. Well, as it comes to simulation, why are we interested in circumbinary disk? Because before 2016 or so, most analytical or simulation results actually hint that binary will experience inspiral instead of outspiral, which is consistent with a previous planet disk interaction theory, which is that the trailing density wave excited by the binary companion will actually extract an angular momentum. But recently, actually around 2016 or 2020, several groups found that the binary will actually outspiral instead of inspiral. This is found by very long-term hydro simulation, mostly carried out by a group of Professor Dong Lai. And more recently, people found that if you change several parameters of the binary system, such as the eccentricity of the binary, the disk aspect ratio of the circumbinary disk, or the mass ratio of the binary will still go to Inspiral instead of Outspiral. So this is actually still an open field, because people are debating that binary will, whether the binary will generally go Inspiral or Outspiral. And this is actually yes, this is still actually an open field. So what we did in this study is that we explored the effect of thermodynamics on circumbinary accretion. Why we are interested in thermodynamics is because most of the previous studies are actually using this kind of locally as a thermal equation of state, which means the temperature is actually a fixed function of the radial distance. So we are not allowing any kind of thermal relaxation in previous simulations, which is actually a very crude approximation, because we know that actually the disk temperature in realistic situations will be how can I say, dominated by the balance of viscous heating and radiative cooling. So we do not expect a constant temperature in a certain radial distance. And another thing we wish to study, another reason we wish to study this kind of role of thermodynamics is because a recent work did by Miranda and Roman Rafikov found that the density wave can behave very differently in planet-disk interactions. As you can see, this is actually a perturbed density profile in planet-disk interaction. And when the cooling time is different, you see the density wave actually behave very differently. Especially the density wave will exhibit strong dissipation when the cooling time is actually proportional to local Keplerian timescale. And our first hydro simulation is actually a very primitive one, because we use the grid code Athena++ and 2D cylindrical coordinates. And as you can see, we actually excise the central simulation domain. Say the two small mini disks are actually not included in our simulation, in our first simulation. And we use the diode boundary condition so that the flow are only allowed to flow outside from larger radial distance to inner radial distance, and this kind of outflow from the inner boundary is not allowed. And what we did in this study, I'll say the novel point in our first study is that we changed the equation state from locally isothermal to dynamical cooling. Say we allow a finite cooling time, which is proportional to local Keplerian timescale, which is the dynamical cooling introduced by Gami et al. In 2001 paper. And this effective cooling time beta is actually the only parameter in our first study. So when beta equals to 0, we go back to the ideal local isothermal limits, which the temperature is always constant in a certain radial distance. And when beta is larger, we allow a finite time thermal relaxation. As you can see, this is actually our first result, that from left to right, you gradually increase the cooling time beta and basically go from locally isothermal limits to gradually go to adiabatic limits. And the circumbinary disk cavity gradually change from eccentric to circular. Actually, first change from aligned eccentric mode to twisted eccentric mode, then to perfectly circularized cavity. And if you're focusing on the accretion variability, actually there is a prominent change associated with the change in morphology, is that when in the locally isothermal limits, you have two kinds of accretion variability, which is the first one is the fast accretion variability, which is around half of the binary orbital period. That fast accretion variability is associated with this kind of narrow accretion streams, because when binary repeats itself every half orbits, this kind of accretion variability will also repeat itself. So that's why the fast accretion variability is around half of the binary orbital period. And there is also a relatively long accretion variability, as you can see, which is around 5 times binary orbital period. This one is associated with the disappearing and reappearing of this kind of high density lump, because the orbital period of this high density lump around the binary cavity is around 5 times binary orbits. So that's why you have the longer accretion variability, which is around 5 times binary orbital period. And when the cooling time is gradually increasing from left to right, you can see the accretion variability is gradually suppressed. First is that this kind of 5 times orbital period long-term accretion variability disappears when beta equals to 0.7, because this kind of morphology is actually fixed, and you will only have the half times the binary orbital period's variability. Well, perhaps I can re-emphasize that this part. Previously, in the local isothermal limits, you have this kind of long-term 5 times orbital period variability, because this high density lump will appear and disappear in its local Keplerian timescale. But when you have a larger beta value, when beta equals to 0.7, this kind of morphology actually will fix and only rotate or precess around the cavity wall. So that's why the long-term variability disappear, and you only have the variability associated with the accretion stream connecting from the circumbinary disk to the inner cavity. And if you increase the cooling time to a very relatively larger value, when beta equals to 0.1.0, this is actually the case when the cooling time equals to the local Keplerian time. Actually, the accretion variability is totally suppressed. That is because in this scenario, there will the morphology of the disk will basically remain the same and only correlating with the binary. So no variability in the morphology actually implies there is no variability in accretion streams. That's why we do not have any kind of variability in beta equals to 1 case. And back to our original story, we are caring about this problem mostly because the angular momentum transfer between the binary and the disk. And how can we measure this problem is that we can measure the angular momentum flux transfer from the disk to the binary. Well, in a standard accretion disk theory, the advection is actually is the angular momentum carried by each fluid parcel from a larger distance to the radial distance, to the inner distance, which is actually cause the binary outspiral. And the viscosity and gravitational interaction is actually removing angular momentum from the inner region to the outer region. Well, so in the circumbinary accretion case, this is very similar. So we saw the advection torque is actually making the binary outspiral, and the viscous torque and gravitational torque are the two components cause the binary inspiral. And how can we find the threshold for binary outspiral and inspiral is actually we can, I didn't show it here, but we can actually do a time derivative of the binary orbital energy, specific energy, and found the binary semi-major axis will whether the binary semi-major axis expand or shrink as time goes on. This value will only depend on the specific angular momentum, say L0, or on a specific its relation on a specific value, or say 3/8. And that is not dependent on the accretion rate, because the accretion rate is always positive. Okay, so that was a bit complicated, but we can just show the result here is that this horizontal green dot dashed line is the threshold for binary accretion, binary inward migration and outward migration. And you can see in the local isothermal limits, when beta equals to 0, you will only have binary Outspiral. And when beta gradually goes to larger value, the angular momentum transfer between the binary and the disk will actually decrease and allow a small window for binary Inspiral. In other cases, you will always have binary Outspiral. You can actually neglect all the detail here because these are a series of convergence tests we did. So for a general conclusion here is that for most cases, you will still have binary Outspiral instead of binary Inspiral, but there is a very small window that allow inward migration of the binary because the circumbinary disk to happen. Perhaps there is a quite interesting result is that we also found a degenerate solution or hysteresis in our simulation, is that your final conclusion, or say the final result of angular momentum transfer, can depend on your initial condition. And this I will mention later, but I will not emphasize that here because this can be dependent on our simulation geometry because say we excise the central cavity that can change, that can be the reason for the degenerate solution to happen. Okay, well, that's the end of the first study because, in 2D cylindrical coordinates, we excise the central cavity. That is the major limitation of our first study. And in our follow-up study, we changed the simulation geometry from cylindrical to Cartesian, and that allowed us to resolve the entire simulation domain, especially the co-orbital region of the binary itself and the two small mini disks around the binary. And in this work, we use adaptive mesh refinement, which can allow us to explore this problem both in a very large radial distance and also resolve the inner region of the circumbinary accretion with very high resolution. We still use the same scheme, which is dynamical cooling, and you can still use beta as an effective cooling time. Well, we still use the same temperature profile, but this is not a very significant case here. Well, I will, well, there is, perhaps it is a bit confusing, but please bear in mind that we did a very thorough parameter study on thermodynamics and also on viscosity profile. So I will mention that later why we use different type of viscosity, but this is very important because we tried basically two different kinds of viscosity. The first is the constant viscosity, which means your viscosity is a constant independent of radial distance. And the second is the standard alpha viscosity, which is dynamically varying with the local temperature, which is actually the standard viscosity used by most people doing accretion disk. Well, the difference between these two is that as time goes by, when thermal relaxation is involved, this kind of alpha viscosity will have a varying temperature profile, which will modify the viscosity profile. So the difference between the two is actually not showing these profile. The most significant difference between the two is actually the first constant viscosity is a static kind of viscosity, and the second kind viscosity, the alpha viscosity, is the dynamically varying with kind of viscosity. So the second kind of viscosity will co-evolving with the simulation, or say co-evolving with the temperature. So that's why our title is the balance between heating and cooling. That is the case of alpha viscosity. You need to reach a new balance between viscous heating and our thermal relaxation. Yes, and how to distinguish the case of binary Inspiral, Outspiral? We can still use our old method, which is measuring the angular momentum transfer across the circumbinary disk. by measuring different components, as I said before. And because we also resolve the inner region, especially the binary co-orbit region, we can use a new method, which is the direct torque calculation on the accretion. Well, perhaps a very basic introduction on this is that we know in simulation, how do we measure this kind of binary outspiral or inspiral? For the binary itself, they only see two kinds of interaction. The first kind is a short-range interaction, is the accretion process acting from the mini disk to the binary component. And the second is the long-range gravitational interaction integrated across the entire domain. So actually, you can do a single value calculation combining this effect of accretion and gravitational interaction. So in the end, you will have a single value varying with time, which controls the binary migration. And the second method is the same as I introduced before, is that we can measuring different components of angular momentum flux, advection, viscosity, and gravitational interaction, and finally have a radial profile which control the binary inward migration or outward migration. Well, we use these two kinds of methods in order to verify our results. That you can see this yellow dot dashed line, horizontal yellow dot dashed line is the method, is the first method, is the result calculated by first method. And this orange line is the radial profile calculated by second method. They reach a very nice agreement with showing our result is actually convergent. Okay, so I will introduce some basic results. First is the constant viscosity case, which means, well, I will emphasize again that this is the case you have a static viscosity profile. And the trend of the morphology change is actually similar to the previous study, that 1 beta goes larger from 0 to 4, still from the case of localized thermal limit to gradually go to adiabatic, but 1 beta equals to 4 is still far from adiabatic, because the adiabatic limit is actually beta equals to infinity, plus infinity. And from left to right, you actually have a larger degree of thermal relaxation. And the trend is still similar. You will still go from eccentric cavity and have a twisted eccentric cavity, this kind of twisted feature around the binary cavity. And in the end, the cavity of the circumbinary disk is circularized as the temperature of the cavity increases. This is actually easy to understand if we also include the temperature profile. As you can see, when the temperature, or say when the degree of thermal relaxation gradually increases, your temperature of the inner cavity will also gradually increases. And in the end, this kind of hotter cavity will circularize the central cavity. And there is actually a very interesting feature we found in this kind of simulation is that 1 beta equals to 4. Our previous conclusion is actually no longer valid because, as I said before, in our first study, 1 beta gradually goes from 0 to 4. The accretion variability is suppressed. But when we resolve the inner cavity with a Cartesian coordinate, things actually change. You can see this is a movie of the actually 30 orbital times binary orbital time scale, which shows a quasi-periodic variability of the circumbinary disk. Changes from this kind of one-armed large-scale spiral feature to two-armed tightly wounded narrow spiral features. This kind of morphology, quasi-periodic variability, will actually modulate accretion and cause a large accretion variability when beta equals to 4. And in order to qualitatively measure this feature, we can measure the mass quadruple of the entire disk and the eccentricity of the entire disk. You can see there is this kind of very nice long-term modulation, which is around 30 times binary orbital period, and that is the basically that is the period of quasi-periodic variability. Okay, back to our original purpose, which is the angular momentum transfer. We can still show this results dependence of angular momentum transfer on the cooling parameter beta. This blue horizontal dot dashed line is the threshold for binary expand or decay. You can see in beta, in the local isothermal limits, they have the binary expansion, and when beta gradually increases, different from previous case, the binary will actually directly go to the regime of Inspiral. And when beta equals 4, you have the largest degree of binary Inspiral. And go to the second case, which is alpha viscosity, or say a dynamical variant viscosity. This is actually the viscosity we use in the first study. So the results is actually similar. Your morphology change actually goes from eccentric to twisted eccentric, or say a little kind of spiral around the cavity wall, and then go to a perfect circular cavity. So this is basically a similar feature, because as time, when the degree of thermal relaxation increases, you have a hotter cavity, and the cavity wall is gradually circularized because of the same reason. And now the angular momentum transfer is actually the same as the previous study. You experience a kind of non-monotonic relation between angular momentum transfer and the cooling time beta. And there is a very small window allow the binary Inspiral. But for other cases, whether beta is small or large, you will always have this kind of binary Outspiral. Well, it is actually a pity that I think there is no analytical theory for binary migration, because the strong non-linearity evolved in this kind of hydro simulation. But instead, we can actually formulate a kind of linear theory for this kind of morphology change in circumbinary disk. You can see this is actually the case of local isothermal limits. The cavity is eccentric and aligned. And when your thermal relaxation is involved, it will first transfer to this kind of twisted cavity, or say twisted density lump. And this kind of morphology is actually captured by a very nice linear eccentricity equation. Well, this equation is formulated by Professor Gordon Ogilvie and others. And you can see this kind of eccentricity equation is a kind of perturbed, slightly perturbed Keplerian orbit. And this single ordinary differential equation comes from the Navier-Stokes equation and also the continuity equation. And we assume a very small disturbance of the perfectly circularized orbit, Keplerian orbit, and use the eccentricity vector to characterize this kind of deviation from circular orbit and from this kind of eccentricity equation. And you can see we can enroll this non-thermal, non-ideal equation of state through two terms, say a balance between adiabatic effect and isothermal effect. And the perturbed density profile actually match very nicely with the simulation result. Well, these are actually still the same figure. That on the left, you have the one-dimensional eccentricity and the arguments of pericenter. And on the right, you have the two-dimensional profile. These two are actually the same, but showing in different manners. in the local isothermal limits, you have this kind of, well, I should emphasize that this is a perturbed density profile. In order to match simulation, you will need to add a background density profile. So this kind of red region shows the density enhancement, and the blue region shows the actually density should be lower than the background density profile. So this plot actually shows the case you have a aligned eccentric cavity, which is consistent with this kind of simulation. And when beta gradually goes to a larger value, especially when beta is around 1, here gamma is the adiabatic index, which is 1.5, or say 1.6 in our simulation. You can see this kind of twist, which is also consistent with simulation. But when it goes to adiabatic region, you will still have this kind of line eccentric profile. Well, you perhaps will say this is inconsistent with your simulation because your simulation shows when beta goes to larger value, you have a perfectly circularized cavity instead of eccentric cavity, right? Oh, that is because we can also calculate the damping rates of this kind of eccentric mode. You can only focus on the lower panel on the right here. Is that when beta equals to, well, this is actually the region when beta is around the local, around 1, say, the cooling timescale is similar to local Keplerian timescale. So this is the case when you have the largest damping rate, which means your eccentricity of the entire disk is damped very efficiently. So the damp of eccentricity of the disk, which means you're only left with circularized Keplerian orbits. So this is the case. You only have a circular cavity. So this is consistent with our simulation because in the local isothermal limits, you have aligned eccentric cavity. And when beta, or say effective cooling time, gradually increases, you have the increasement of the disk, of the twist. And when beta is around the local Keplerian timescale, you will have this kind of most effective damping. Say here is when you have the circularized cavity because the damping of eccentricity. Well, we can also calculate the self-gravitating case, but this perhaps is, we can postpone that if you have more questions. As for technical issues, well, in my simulation, there are only 2 problems which prevent me from doing this project smoothly. The first is always do a lot of convergence tests before production runs. This is, everyone knows this, but well, I have to say, must be very, very careful, especially when you have a lot of mesh refinement, especially adaptive mesh refinements and static mesh refinements. So adaptive mesh refinements can be used as some sort of static mesh refinement with changed boundary shape. So that is one you need to very, very careful about the convergence test. And the second one is for highly viscous system. Actually, problem can be your simulation is stuck with a very, very small time step because this diffusion source term is actually not a hyperbolic term. So that is the case when your delta T due to the effect of diffusion is proportional to delta X squared instead of delta X. So that is the case. Your Keplerian velocity is, say, the delta T of your simulation limits by your flow viscosity is proportional to delta X instead of delta X squared. But when you have a highly viscous system, actually the effect of viscosity can limit your time step very significantly. So how to solve this problem? The first is turn on super time stepping. So that is the case when you calculate the viscous effect and the ordinary hydro simulation separately. So you can actually have like 10 or 20 subcycle of hydro calculation and 1 subcycle of viscous calculation. And the second one is to change the simulation geometry. So as what I did is change from cylindrical coordinates to Cartesian coordinates. Actually, this problem is mentioned by Professor Oliver Porst before, is that if you use your cylindrical coordinates and extend the simulation region to the pole, actually the innermost region will significantly limit your time step. So that is why change to Cartesian coordinate is a lot better. Well, my take-home message is actually very short, is that for circumbinary accretion, if you enroll thermal relaxation or say a dynamical cooling, a longer cooling time essentially makes your cavity hotter, and this leads to a symmetric cavity or quiescent accretion rate, accretion variability. And this binary migration can significantly reliable on the viscosity profile you choose in your simulation. If you choose a constant viscosity or say a static viscosity profile, this will generally lead to binary inspiral. And if you use a dynamical varying alpha viscosity, the relation between cooling time and the binary migration is actually non-monotonic, will lead to a deep angular momentum transfer. And this is actually a funny picture because I took this from the Mandalorian 2. And this planet is actually the most famous planet in the world, which is Tatooine, the birthplace of Luke Skywalker. Well, that's basically all. Thanks.